Hello, everyone. How are we doing? Can you all hear me okay? And sorry we're slightly late. Thanks for sticking around. You can hear me. Perfect. Great news. Is everyone doing all right? Well done for getting out and doing some physics on a Sunday. This will be all the physics I do today, that's for sure. But yeah, thanks very much for coming. So today is circular motion, which is usually, maybe it depends on the exam board, but usually it's a second year topic. But the stuff that we're doing will, I would say, because it's the first part of circular motion, if you haven't seen it before, and you're in your second year, then that's absolutely fine as well. Hopefully this should make sense. Anyway, feel free to ask any questions that you have along the way. It's great if this is interactive as possible. So if you don't understand anything, or if you have any questions, even if they're a bit off tangent, you can put them in the chat, and I'll try and answer them the best as I can. There's also going to be exam questions in here that we can have a go at together as well. Okay, so let's get started. Today is about circular motion. Hopefully you can all see my notes. So, yep, that's a picture of me there. And this, so my name is Matt. Head of physics here at Snaprovise. I'm a physics PhD student, although I've actually snuck into the computer science department. But I do physics there, but undercover. And yeah, I've been tutoring A-level physics for at least the last 4 years. Good. Okay, so if you enjoy what we do today, we're doing a lot more of these sessions on the Snaprovise website. So if you want to, you can sign up to Snaprovise. You can get a 1-week free trial where we'll be doing, I mean, I'm actually doing another web class tomorrow. So yeah, and we have a code here that you can use at the checkout. And hopefully see some of you there. Anyway, so today our objectives are all about circular motion. I'm just going to take a look at the questions. Year 13, Year 12 student, guide you how to study maths for Year 12. So it's pretty general. I mean, there's a lot of stuff you're going to need to do. I'll give you maybe the same bit of advice you hear from a lot of people, which is, especially with maths, you can't just read the textbook and memorize it. Like, you've really got to spend a fair bit of time doing exam questions and just trying to do the problem solving yourself. That's the way to get the math stuff to stick. Loads and loads of exam papers. Okay, so objectives today are to define radians and angular velocity, understand things about centripetal acceleration and forces. To be honest, there's going to be some conceptual stuff we'll talk about with centripetal acceleration. The main thing is we're going to learn the formula as well. And we'll look at some examples. I guess that's the conceptual bit. Okay, so there are 2 types of things that we're going to need to know going into today's session. One of them is a maths thing, and it's going to be about angles and circles. The other is a physics thing, and it's going to be about Newton's laws. So let's start with angles. So we're going to start up, we'll introduce radians, but we're going to start off thinking about degrees as the units by which we measure the angle through which something is turned. So just to get us warmed up, can anyone tell me what each of these 3 angles are? So we've got angle A here, angle B here, angle C here. So I'll start us off. Let's say angle A is 90 degrees. This is a perpendicular angle, a right angle. So what are the other 2? Just to get us warmed up. Great, so A is a right angle, B is 180 degrees. Absolutely right. If you like, it's like doubling this one, right? It's like adding another one of these right angles on. And so double of 90 is 180. Good. So this is 180 degrees. And the last one is 360. Yeah, really good. Nice. So 360 degrees is a full circle. If you like, that's kind of like the most important angle. Okay. So separately from angle stuff, we're going to need to know some properties of circles. There's about 2.5 things that you can ask about a circle, maybe 3. So here's my circle. There is the length from the center of the circle to any part of the edge of the circle. So I want to know what that symbol is. Well, I'll give you the symbol. It's R, but I want to know what name that is. And then there's the length going all the way around the outside. All the way around. This is given the symbol C. So R is the radius. And C is the circumference. Okay, good. Yeah, radius and circumference. And the big thing we're going to need to know is some relationships between these things. So in particular, the circumference is always equal to 2 pi times the radius. So pi is just a particularly special number, but it's just a number and you can find it in your calculator. The second thing we want to know about is the area of this circle. How much space does it take up? And so the area is usually given the symbol A. And again, it involves this, this strange symbol pi, and it's given by pi times the radius squared. So these are going to be 2 formulas that we need today to talk about circular motion, which makes sense because they are the basic properties of circles. So that's the maths, and the ideas we're going to mix this maths with are the physical ideas of Newton's laws. So Newton had 3 laws, and they come in an order. Can anyone tell me what those laws are? So let's start with the first one. I'll say, I'm going to phrase it as an object. I might leave some stuff blank. An object will remain at something unless acted on by a resultant something. Good. So rest is part of it. I prefer a slightly more general version of it. So you could absolutely write rest here. The other thing you could have written, which is a little bit more general, so I'll write it a bit smaller, at rest or constant velocity. The reason I like that bit of the law is it's the less intuitive bit. Good. Unless acted on by a resultant force. Absolutely right. So forces are the kinds of things that change how objects move. So in particular, what's important is, let's say I have some object and it's moving along at some velocity v. It will continue to move at that velocity v unless I act on it with some force. Now, this is a bit counterintuitive if you've ever thrown a ball in the air, because if you've ever thrown a ball through the air, you know that it slows down, its velocity does change. But the reason for that is that there is a resultant force on a ball when you throw it through the air. That resultant force is the force of air resistance that's pushing it backwards. Okay, so that's why this first law was so hard to find, because we live in a world with air resistance. Okay, so the second rule says F is equal to ma, where F is the resultant force and A is the acceleration. And m here is the mass. So, okay, this actually entails the first law, in that when the resultant force is 0, this tells us that mass times acceleration must be equal to 0. And if the acceleration is 0, that means you'll move at a constant velocity. Okay, finally, the third one. I think Wombat has already put the third one in, so that's really nice. Two objects apply a force of equal magnitude, opposite direction, same type of force and line of action on each other. In the exam, you wouldn't get full marks for just stating the equation. You need to say what the symbols in the equation mean. So you could say F equals ma, where F is the resultant force, m is the mass, and a is the acceleration. Then you'd get full marks. Okay, yeah. So the third law has a kind of a catchphrase, I guess. Every action has an equal, opposite reaction. So this one won't be as important today, but essentially what this says is if I ever push on something, so here's my hand pushing on my arm, then, okay, I have this thing exerting a force on this thing, then my arm, the thing having a force exerted on it, will exert a force back. And that's what I can feel in my hand. My hand pushes on my arm, and equivalently, my arm is actually pushing on my hand. Okay, good. So those are the three laws. So in terms of spec points, you're going to need to know the circular motion stuff no matter your spec. Yeah, looks like for AQA, it's A level, so second year. Here it is in OCR. So we're going to be covering all of those formulas today. And same here for Excel. Good. Okay, so let's get this started. Radians and angular velocity. So this is all going to be about how we describe motion in a circle. And then the second half will be all about how we figure out what kind of circular motions will actually happen. So a radian is a new unit of angle. Usually we measure radians in degrees, where you have 360 degrees in a circle. A radian is a new unit of angle, different to a degree, so that there are 2 pi radians in a circle. So it's often defined in a different way, and I'll write that here. A radian is the angle which gives an arc length equal to the radius. So there's a lot to unpack there, because we have to say what on earth this arc length thing is to start with. Okay, so let's say I have some circle, and then I look at the center of the circle, and I look at 2 points on the circle. So here's point 1 and point 2. Let's write it like this, point 2. Then whenever I choose 2 points in the circle, I get an angle. Let's call that angle theta. Well, we know that each of these lengths here is r. And we have some length here, the length of this curve that goes around the edge of the circle. Now, if it was all the way around, it would be the circumference. It's a bit of the circumference. Now, if this length here is r, so this is the arc length, if the arc length is the radius, then we say that the angle is 1 radian. The arc length could have been a different length. For example, it could have been 2 lots of the radius all the way around here. Or it could have been all the way around here or something. But when the arc length is 1 radius, the angle is 1 radian. So that's the definition. Okay, so now we can say a couple of things. First of all, with degrees, just to remind ourselves, we know there's 360 degrees in a circle. Does anyone know how many radians there are in a circle? I did very briefly sneak it in earlier. There's so many radians in a circle. How many radians is it to go all the way around? Two pi, perfect. 2 pi radians in a circle. Good. What this actually means is that 1 radian, so this is for conversion, so this is a handy rule to know. 1 radian is given by 360 divided by 2 pi degrees. So if I give you 5 radians, you can tell me how many degrees that is by timesing 5 by this number here. Perfect, really nice answers, good. So similarly, does anyone know what 1 degree is? So 1 degree is given by flipping the fraction. So we get 2 pi over 360 radians. So let's just do a quick example of using this conversion formula so that we know we've got it down. Let's say I have 45 degrees. That's a classic angle. It's an important angle because it's a nice fraction of 360. And I want to know how many radians that is. How do I figure that out? Well, I know 1 degree is this many radians. So 45 degrees is 45 lots of 1 degree. So 45 lots of 2 pi over 360. And if I chuck this into a calculator, or in fact, I don't even need to chuck it into a calculator. This is quite a nice one to do by hand. We have 2 times 45, so that's 90 pi over 360. Now 90 over 360, you can check in your calculator as 1 over 4. So 45 degrees is pi over 4 radians. That's useful to know. Good, yeah, quarter pi, perfect, well done. Okay, so that's pure maths. There's nothing to do with physics yet. First bit of physics is talking about how fast something is moving. And before doing that, we're going to talk about how far something is moved along a circle. So angular displacement is simply the angle through which an object has moved. So let's say, for example, that I have some radius r here, r here. I'm moving around some kind of a circle. Oh, I didn't draw that so well. There we go. And let's say that I've moved from this point to this point. Whatever this angle is here, it's my angular displacement. Now, the good news is there's a formula for the angular displacement in terms of other things in this diagram. In particular, if you know this length here, this arc length, let's call it S, then your angle, your angular displacement in radians is given by S divided by R. And this makes sense, actually, because when S equals R, what does that give us? That gives theta equals R over R, which is equal to 1. Great. So this is our angular displacement in radians, because when our arc length is 1, our angular displacement is 1. Perfect. So now we're going to imagine something moving around in a circle, and we want to talk about how many times per second, how fast it's moving around in a circle, if you like. So the angular frequency is the number of radians an object travels. Does anyone know the formula for this, by the way, while I'm writing this? Feel free to type that in the chat. The number of radians an object travels per second. Anyone know the formula for this? So there's a couple of different formulas. One of them is essentially to give a definition. And the definition is to say, okay, well, let's assume that in some time t, I've managed to go round by some angle theta. Well, the definition says it's the angle that I get through per second. So one way of thinking about angular frequency is it is simply angle traveled in a second, angle traveled in some time t, divided by the time to travel that angle. Now, there are loads of other formulas for this as well. For example, we know the time it takes to go all the way, well, we don't know the time. We have a special word for the time it takes to go all the way around the circle. So does anyone know? Well, I'll write it here. Time taken to go 2 pi radians is, well, that's the time it takes to go all the way around. So that's the time period. So one formula for the angular frequency is to take the number of radians it is to go all the way around a circle and divide by the time it takes to go all the way around a circle. And the great thing by that is, as I've already seen in the chat, yeah, really nice. We know that 1 over the time period is always equal to the frequency. So another way of writing the angular frequency is 2 pi times the frequency. Perfect, really nice. Good, okay. So the last bit of learning that we need to do before we do some exam questions is about angular velocity. Okay, good. So in particular, actually, it's about converting between angular frequency and essentially normal velocity. So we're going to talk about the term instantaneous velocity. And this is the actual velocity in the normal sense an object has as it moves in a circle. Perfect. Okay, so we have a formula for this. Feel free to type it in the chat if you know the formula. So if we think about what the velocity is, okay, it's distance divided by time. And what direction is this thing moving in? Well, it's essentially moving around the circle. So the distance it travels is some kind of arc length s. And then, well, okay, so the velocity will be the arc length it travels in some time t. Let's call that s, divided by that time t. Now, let's say we know the angle that a particle has traveled through. So we're going to try and mine a couple of other formulas out of this one now. Let's say we know the angle a particle has traveled through. And we know the radius. Well, we know that theta equals s over r. So therefore, s equals r theta. So then we have this thing being equal to theta r over t. And the great news about this is this theta over t bit is a quantity that we defined in the previous section. Theta over t was this angular frequency. So we have a very convenient formula, which is normal velocity is given by angular frequency times radius. So this last formula here is really worth remembering. Okay, so how is everyone feeling? This is straightforward. Hit a 1 if it's straightforward. Hit a 2 if it's all right. Hit a 3 if it's super confused. And ask me any questions if you have any. How's it sounding? 2, okay. A 1. 1.5, a 2. Okay, nice. Well, do let me know if you have any questions. In the meantime, let's do some exam questions. And a smiley face. Awesome. All right, first one's about the Hubble telescope. It was launched in 1990 into a circular orbit near to the Earth. It travels around the Earth once every 97 minutes. Calculate the angular speed of the Hubble telescope, stating an appropriate unit. So I just want to mention that angular speed is another word for angular frequency. In other words, what they want us to find is that symbol W. You'll see a few different words for it. Okay. So so just one thing to repeat then on this last part. What we found here was the instantaneous velocity, and it was equal to r times the angular velocity. That's the main takeaway of that page. Okay. So we're asked to calculate the angular frequency of the Hubble telescope, stating an appropriate unit. Well, let's see what we've been given. We've been told that this telescope goes once around the Earth. So it goes in a full circle every 97 minutes. In other words, the time period is 97 minutes. Okay, well, we have a formula for the angular frequency. The angular frequency is equal to 2 pi divided by the time period. Now we're told we can use, whoops, 1 second. Sorry about this. So I just had a tech issue there. We'll be back on in a second. You said the focus is a bit out. Has it improved at all? Is it still how it was? If you need me to say more clearly anything that's gone a bit blurry, then just let me know. Okay, so hopefully you can all see the notes again. We're allowed to choose any unit, well, not any unit we like, but an appropriate unit. And we're going to find that leaving all the units as they are is going to be a fine unit. I'm not really sure I can make it sharp on my end, I'm afraid, sorry. But do let me know if you need me to read anything. Okay, so we take our 2 pi at the top, that's in radians, and let's just divide by 97 minutes. If we chuck that into a calculator, we get 0.06477. And what's the units here? Well, we had radians at the top and minutes on the bottom. So that's radians per minute. Perfect. Okay, so next question, and this is quite a nice one actually. The diagram shows a car traveling at constant velocity. Okay, so it's moving along at some velocity v. When the tires are correctly inflated, the effective radius of each wheel is 28 centimeters. So, okay, let's draw that on. Here we have 28 centimeters. Okay. Calculate the period of rotation of the wheels when the car is traveling at 21 meters per second. So we were allowed to leave it in an appropriate unit. You could have converted it to seconds, but it was fine as it was. The main thing was you just needed to state which unit you had used. So the important thing was I just said it was radians per minute. Okay. So for this question, what do we know? We know a V. That's great. We know an R. And now we need to try and find a formula that involves V and R and the period of rotation. T is the thing we wish we knew. Okay, well, what do we know? Well, let's start writing down some equations and see if any of them are useful. We know V equals omega R. Okay, that's a good equation. It involves these two. What about this omega? Well, we don't know omega, but omega can be written in terms of the time period. So this is good news. We know that omega is equal to 2 pi over t. So if we put these two formulas together, we get a formula that has the three quantities we're interested in. So we find that V is equal to 2 pi times over t multiplied by r. And now the thing we wanted to figure out was the rotation. So let's rearrange was the period of rotation. So let's rearrange for the period. We find that the time period is equal to 2 pi times r divided by the velocity v. Okay, so now we have everything we need and we can just chuck this into a calculator. I'm going to change the units here. So go from centimeters to meters. So we're going to say V is equal to 2 pi times R, which is 28 times 10 to the minus 2 meters. And then we're going to divide by the velocity, which is 21. If you chuck that into a calculator, you should get around 0.084 seconds. Yes, seconds. Good. Okay, so hopefully that makes sense. And that's quite a powerful question, that one. We're just told the speed of the car. We're just told the radius of the wheels, and we could already find out how many times the wheel goes round per second. Or how long it takes the wheel to go round, sorry. Okay, good. So we've started putting a bit of physics into the circular motion stuff, but not all of it yet, because at the start we talked about Newton's laws, and so far we haven't introduced Newton's laws into this equation at all. So that's what we're going to do now. So we're going to define a notion of centripetal acceleration. So I'll write down what it is first and then explain what it means. Centripetal acceleration is given by the formula A equals V squared over R. And you can show that that's equivalent to R times omega squared. Okay, so what is centripetal acceleration? It is the acceleration that you must have if you're going to go round in a circle at some velocity v at some radius r. So here I am in a circle, moving around with some velocity v at some radius r. Then, if I'm doing that, there must be some acceleration that's pulling me towards the center of the circle. Why? Because while my speed isn't changing, my velocity definitely is. Over time, my velocity keeps changing direction. And if my velocity is changing, that means there must be some kind of acceleration. Now, this acceleration, it turns out, needs to be directed towards the center of the circle. And to move around with a velocity v at a radius r, your acceleration has to have this magnitude. So that's the main theorem. That's the main thing that we need to know. Okay, the other thing that we need to know is the direction. As we mentioned here, the centripetal acceleration is directed perpendicular to the velocity. In other words, to the center of the circle. Acceleration always points towards the center of the circle. Okay, now you may remember Newton's second law, so that's going to be the big one for us today. Newton's second law says force, the resultant force required to achieve some acceleration, is given by mass times the acceleration. Okay, so the force required, and the force is going to be towards the center of the circle as well. The force required to keep something going around in a circle at velocity v and radius r is given by m times a, and a is this thing here. So it's given by mv squared divided by r, or equivalently, mr omega squared. So that's how we get Newton's laws into circular motion. And that's going to be the big formula for today. Now we'll do some exam questions where, well, we'll do an exam question where we use the formula. But let's just look at some examples first. So we're going to look at some examples of centripetal forces. Centripetal forces are forces towards centers of circles that allow us to move around in a circle. So for example, let's say I'm swinging around a ball on a string. What is the centripetal force? What is the force towards the center of the circle that is causing this object here to keep changing its direction and move around in a circle? What force is it? It could be a force like, just to give examples of the kind of things, you know, forces like, is it a friction? Is it a gravitational force? Is it a electrostatic force? Like what kind of force is causing this ball to go around in a circle? Tension in the string, perfect. Yeah, we have a string here. And tension in the string is going to go along the string. In other words, tension in the string is going to point towards the center of the circle. So that's perfect. And it's the only force. So yeah, ball on a string, the centripetal force is tension. Perfect. Okay, let's say I have a satellite orbiting the Earth. So this is kind of a weird one because there's no contact between the Earth and the satellite, but the satellite, which would in principle want to escape, keeps getting pulled towards the Earth. There's some kind of force that keeps pulling it towards the center of the Earth. What's this force? What is the centripetal force for a satellite orbiting the Earth? Gravitational force. Perfect. Absolutely right. There is a gravitational attraction between the satellite and the Earth, and that provides the centripetal force. Gravitational. Perfect. Okay, I really like the bottom left example. What is the centripetal force when a car is going around a bend? So we've got a car going round in what could in principle be a circle if it stayed on a roundabout or whatever. There's got to be some kind of force pulling it towards the center of the circle. What could that be? I think this is maybe the least clear one to think about. Really nice. Yeah, it's the frictional force. What's happening is, the car would in principle like to keep going in whatever direction it's going. Because it's turned its wheels a bit, the kind of wheels are kind of just like being dragged outwards in that direction, and they're being dragged like against friction. Friction is actually like pushing, essentially kind of trying to push these wheels back into the center. So yeah, car going around the bend, centripetal force is friction. You can feel this, for example, if you're sat in a car that's going around in a bend. If you think about when you're going around a bend in a car, you're sat there and kind of, it's like your body tries to lurch outwards, but you'll feel it's kind of where you're sat, you feel a kind of pull towards the center. And that's essentially because your seat is exerting a frictional force on your body, pulling you back in. So with those kind of situations, it's friction. Now, Ferris wheels are an interesting and slightly more ambiguous one. So what kinds of, there's actually more than one answer to the kinds of forces that are giving you a centripetal force here. So Ferris wheel, I've got some carriages going around, something like the London Eye, for example, or just any of these kind of circus rides. What are the forces that can point a carriage towards the center? What kind of forces are there? What are the centripetal forces for a Ferris wheel? Yeah. So this tension or contact force thing, that's a really nice answer. That's the reason I say that this one's slightly ambiguous. So one of those at least, yeah. There's another one as well, something other than tension, and I'll explain those. Well, see if you can guess the other, but at the same time I'll explain this part. So depending on how this Ferris wheel is working, maybe what you have is the Ferris wheel is going around at some pace, and you have these spokes here, and they're attached to these carriages. And so just like swinging a ball around with a string, these spokes have some tension. So let's write tension down, which pulls the carriages back towards the center. What other options are there? Well, okay, there's this contact force. So you might see, for example, it feels like there's some kind of barrier around the outside of these things. Depending on exactly how the Ferris wheel is designed, it may well be that as the Ferris wheel wants to go outwards, there's a barrier, there's some kind of thing above it that exerts a kind of reaction force that pushes it back in. So contact or reaction force. If this contact one doesn't make too much sense, don't worry, because we're going to have an exam question that gives a really nice example of a contact force giving a centripetal force. But there's a third one, Now, the third one is interesting because it's not always towards the center, but sometimes it is. So the third one is gravity. Why gravity? Well, let's take a carriage. Now, let's see when gravity kind of, this is a weird one, right? Let's look at this top carriage here. Gravity pulls this carriage towards the Earth, which is downwards, which is, towards the center of the circle. So when the carriage is at the top, it provides some kind of centripetal force. When the carriage is at the bottom, gravity pulls it away from the circle. So it's kind of like an anti-centripetal force or something. It's clearly involved in circular motion anyway. And then on the sides, gravity is really weird because on the sides, gravity just doesn't pull you towards or away from the center. So depending on where you are in the circle, gravity might be kind of part of a centripetal force. It might be working against a centripetal force. It's kind of a weird one. And again, we'll look at an example of gravity and contact forces working together in an exam question, which I think will maybe make this example clearer. So in the meantime, how's everyone doing? Does anyone have any questions? And how's everyone getting on? Okay. Well, let me know if you have any questions. Okay, sweet. That's nice. Awesome. Well, absolutely no problem if it's not, and do ask me questions. In the meantime, let's do some questions. And this first one is a great question to look at because it's so common in exam papers. A particle that moves uniformly in a circular path is accelerating, yet moving at a constant speed. Okay, so we mentioned this before. Let's draw ourselves a diagram. Particle moves around in a circular path. Okay, it's accelerating. How do we know it's accelerating? Hey. So if anyone is able to say how we know that a particle moving in a circle is accelerating, have a go at putting that in the chat, because that's going to be the crux of this answer. So if you can say how you know it is that a particle moving in a circle is accelerating, then you got this question down. So in the meantime, they do mention something. They try and throw us a curveball. They say, well, it's accelerating. You're going to tell us why. But it's moving at a constant speed. It's always moving at, if it's 5 meters per second here, it's going just as fast over here. Okay. So how can it be accelerating? Good. Acceleration is change in velocity per time. The speed may not be changing, but since the direction of motion is changing, there must be an acceleration perpendicular to the direction of motion. If you learn anything today about circular motion, have it be this. Okay, displacement is changing, direction is changing. Good, yes, so there's a change in displacement. The key thing though is that the velocity is changing. and that means that you have an acceleration. Good. Acceleration is a vector and velocity is a vector. Okay, so that's the conceptual one. We'll do a maths one and then finish with another conceptual one. Okay, so this is quite a good question, this one. And there's a lot of information here. A 1 kilogram mass, they haven't put that in the diagram. Whenever they don't put information in a diagram, I find it helps me to read the question if I put the information in as I read it. So we have a 0.1 kilogram mass here. Okay, placed on a horizontal turntable that's then rotated at a fixed rate. So it's going round, okay, and we have 78 revolutions per minute. What kind of quantity is that? That's going to be the key to this question. We know this is a mass. What symbol would you give this quantity I've put in the rectangle? So I'll keep reading the question, but let me know what symbol that should be. You know, we've seen a lot today. There's been R's, omegas, T's, F's, V's, S's. What letter is that thing? Okay, the mass may be placed on the table at any distance R from the axis of rotation. If the maximum frictional force between the mass and the turntable is 0.5 newtons, okay, so we're going to have a force on our object that's moving around of 0.5 newtons. Now, this is one of those ones where it's a frictional force that's causing a centripetal force. Calculate the maximum value of the distance r at which the mass would stay on the turntable. Okay, so basically they're asking, if you have this centripetal force, what radius will you be moving at? So this 78 revolutions per minute is a very interesting quantity. It is the number of times I go round in a minute. That is essentially a frequency. What is a frequency? A frequency is the number of times you go round in a second. So F equals rotations per second. Here we have rotations per minute. So we just need to convert it to rotations per second and we'll have a normal frequency. So this is an F. Okay, so then let's see what stuff we have going for us. Well, there's force involved. So what's our new formula? F equals mr omega squared. Okay, so we know we want to figure out R. So let's rearrange for R. R will be equal to m omega squared. Sorry, R will be equal to F divided by m omega squared. And then we say, do we know the mass? Yes, we do. Do we know the force? Yes, we do. So what we need to know is omega. Now, omega is given by 2 pi times F. So if we know the frequency, we know omega, and then we know R. So let's first figure out omega. Well, omega is equal to 2 pi times, okay, what's the frequency? Well, we have 78 revolutions per minute, which means we do 1/60th of that in a second. So the frequency in hertz in revolutions per second is 78 over 60. If you chuck that into a calculator, you'll get 8.168, etc. Then for R, we'll plug in all the numbers we have. We have 0.5 newtons divided by 0.1 kilograms, then multiplied by 8.168 all squared. And if you chuck that into a calculator, you'll get 0.0749, or roughly 0.075 meters. And that's your answer. So mathematically, that's a more involved one. The key to these circular motion questions, I used to find, is just to write all the formulas down and then try and see the connections between them. So here I was just like, okay, they've told me a force, so let's write down the formula for force. They've told me a frequency, so let's write down that one. And then I realized I've got everything I need. Okay, so the last one is a conceptual one. And this is a really nice question. Figure 2.2 shows the drum of a spin dryer as it rotates. A dry sock S is shown on the inside surface of the side of the rotating drum. Okay, so there's our sock. Draw arrows on 2.2 to show the direction of the centripetal force acting on S when it is at points A, B, and C. Okay, now this is almost a trick question. Forget whatever forces are actually on the sock. The centripetal force can only go in one direction. What direction is that? It has to go towards the center. So at A, it would go towards the center. At B, it would go towards the center. And C, it would go towards the center. So that's question 1 done. State and explain at which position, A, B, or C, the normal contact force between the sock and the drum will be the greatest. Okay, so I think this is a really nice one to have a guess at first. So we have a sock which is on the surface of a drum. Now, typically it may be wanting to kind of get out the drum, who knows? As a result of being in contact with the surface of the drum will be exerting a normal contact force. Often that's called like R for reaction. So when the sock is here, there'll be some reaction force. Let's draw them all here. There'll be some reaction force here. There'll be a reaction force on the sock when it's here, and one when it's here. Who thinks, have a guess. Do you think the reaction force will be bigger at A, B, or C? One way of thinking about this is, when is the drum having to push the sock the hardest? Or in other words, because of Newton's third law, when is the sock being kind of pulled into the, being kind of pushed into the drum the hardest? Okay, so we have a guess for B and a guess for C. Okay, so we're going to mention a couple of points. First of all, this is going in circular motion. Yeah, so it is something to do with C, and the answer is gravity. And maybe you have this intuition, the people who said C, that like, well, the sock is being pulled down due to gravity, so the drum is probably having to push even harder on the sock. And that is kind of what's happening. So let me first state a rule. The centripetal force i.e. the resultant force must be the same in magnitude everywhere. So let me explain that bit first. So wherever you are, you're moving around in a circle where you have some velocity v and some radius r. And the size of the centripetal force is fixed by that. It's just m v squared over r. So none of these things are changing as you go around the circle. So the centripetal force, the reaction force, has to have the same magnitude everywhere. So let's look at situation A. In situation A, we know that the force has to be of size, let me draw a better circle, of size mv squared over r, pointing downwards. Now we have to ask, how can I make this force? What's actually causing it? Well, there's a force of gravity. So I suppose it's not there explicitly, but it's a washing machine just kind of going around in a circle, and it's you actually have to assume this. The reason essentially is that there's just some kind of motor that's driving the washing machine, and maybe the motor has to push harder at some points than others, but it'll push this thing at a constant velocity. You do have to assume that, I'm afraid. Yeah, okay. So what can we say? Well, here we have this centripetal force. How can we make this? Well, there's two forces acting on the sock. What are they? There's gravity and there's the normal reaction force. Let's call it R. So what we have at the top is the R plus the normal. So the normal reaction force plus gravity, they work together to make the centripetal force. At the bottom, we have something quite different. At the bottom, gravity is pulling the sock downwards. So there's gravity. And what does that mean for the reaction force? Well, now the reaction force has to produce mv squared going upwards whilst working against gravity. So this time we have R all together because they're working against each other. We need R minus gravity to be equal to mv squared over R. So what that means is at the bottom, the reaction force has got to be really big because it's got to overcome gravity and then provide that centripetal force. Whereas at the top, because gravity is helping make the centripetal force, the reaction force doesn't need to be as big. So that's a really in-depth explanation. You don't need to say all that for the examiner. The examiner would say centripetal force must be the same in magnitude everywhere. At the bottom, I should say here, it would be the greatest at C, because yeah, the centripetal force is the same everywhere. And at the bottom, contact must oppose gravity to make a force, to make the centripetal force. Perfect. Okay, so equivalently for the last one, we'll just say that, okay, well, on the opposite side of things, at the top, at A, we have the smallest contact force, and that will be because in this case, R is helped by gravity to make the centripetal force. Okay, so because here gravity works with the centripetal force, gravity works with the contact force rather than against it. Ah, you just started this chapter last week. Okay, well, that's perfect timing. I'm glad to hear it. Hopefully this was helpful then for that. Okay, so let me know if you have any questions. You should now be able to define radians and angular velocity. You better understand about centripetal acceleration and forces and describe examples of circular motion. Let me know if you have any questions. In the meantime, for those of you who wanted to use the startup code that we gave at the start, I just want to let you know a bit about what we're doing on the SnapRevise website. So first of all, if you stay logged in for YouTube, we've got more web classes coming up live here, usually on a Sunday, always on a Sunday. So I'm not sure what the next class will be, actually. I'm afraid I don't know at the moment, sorry. In the meantime, we're doing a lot more classes on the SnapRevise website, which you'll be able to access if you use our free trial code. In fact, I'm doing a web class tomorrow. And so I'm just going to let you know how that looks. So I'll stop sharing my screen. There we go. Good stuff. And now I'm going to share it again. So thanks very much, everyone, for coming. It's been really fun. And thanks for being good and interactive and putting your ideas forward in the chat. That's been really handy as well. So, okay, just to let you know what we're up to on the Snap Revise website, it'd be great to see you there. If you go into Snap Revise and you sign up, then you'll find yourself on our homepage, and then you can access our tutoring services. So there's a tutoring service for lots of different subjects at the moment. I'm currently working, as you might guess, on A-level physics. So we do, at the moment, because we're out of term, we're just doing 2 sessions a week. When term comes in, we'll be doing 4 sessions a week. And they're split into 2 types. There's web classes like we're doing here, where I go through a set piece of material, but you can ask me questions about it as we go through. And, you know, hopefully it always turns into a discussion. Oh, no problem. Cheers for coming. But there's another type of session as well called a drop-in session, which might feel more like the kind of tutoring experience as well. So for drop-in sessions, you can let me know beforehand, or even just during the session, any questions that you're struggling with, any problems that you're not managing to get through, that you need someone to explain and answer to you for. And we will go through them together in the session, and we'll work through the problem and try and get the answer explained to you together during the session. So those are drop-in sessions. And the idea is to take the kind of idea of tutoring and spread out the cost, so that rather than paying so many pounds per session, we say, okay, well, for £50 a month, you can come to as many of our web classes as you like. During term time, that'll be 4+ a week, including 2 drop-ins, which would work out then about £3 a session, which would be much cheaper than standard tutoring. And so, yeah, the goal is to kind of make the idea of tutoring maybe kind of more affordable. So everything's recorded afterwards as well, so you can listen back to the sessions. And here's the schedule for what's coming up. So these ones have happened. As you can see, they're recorded. So tomorrow, I'm working on moments and resistive forces. And so you can come to that if you like, and we can discuss that together. I mean, it's actually quite a nice and somewhat related topic to what we talked about today, which is convenient. The last thing I want to mention is some new stuff. So if you go into our resources section, we've been trying to, so we have online video courses, we've got these tutoring sessions, but we also want to produce kind of a revision materials. So kind of more bite-sized things that you can do in kind of bite-sized chunks here and there. So what we've developed recently are revision cards. So in our revision cards, we have a series of short summaries of each topic. So for example, here we have a description of all the stuff you need to know about photons, the basic equations and the basic conceptual stuff with a diagram. And then what you can do is you can read these cards. And then once you've read the card, you can flip to the back, and to check you've remembered all the stuff that you read on the front, there is a chance to look at a couple of basic questions. So you can read the stuff, flip to the back, have a go at some questions to check you took this stuff in. So those are some of the extra resources you can also take a look at on the Snap Revise website. Thanks very much for sticking around. And I hope that I get to see some of you on Snap Revise. And otherwise, I look forward to seeing you all at the next YouTube session. So in the meantime, cheers for coming, and let me know if you have any questions. Thanks very much for making it such an interactive session. And if you wanted that code, here's the code for a 1-week free trial. So yeah, cheers everyone for coming. I hope that was useful. Let me know if you have any questions. And yeah, thanks for coming. All right. Cheers for coming, everyone. And I'll see you at the next session. All right. Bye.